Hello, Lucia. Welcome. Let's get started with the Biweekly 129. Hello, welcome. Make a square with the same color. You are given a 2D matrix grid of size 3 by 3, consisting only of characters B and W. Character W represents the white color and character B represents the black color. Your task is to change the color of at most one cell so that the matrix has a 2 by 2 square where all cells are of the same color. Return true if it is possible, otherwise return false. And here we have a few examples. So here, example 1, it's true because if we, for example, hello Pat, welcome. Nice to see you. So if we consider, for example, this square right here in the bottom right corner, and we paint this black square to white, then we'll get a square that is all white, so it is true. But here we cannot, right? Because any square that we choose has 2 blacks and 2 whites squares, and here again is true. So notice that yes, and in this one you already have it. You're not forced to change the color. So notice that the only time where we cannot do it, so if we consider a square, so let me go to the drawing board. So every time you have a square, a 2 by 2 square, the only time that you cannot do it is when you have 2. So you have 2 black and 2 whites. Then you cannot make it all the same color with only one, with most one change. So, but if you have 0 whites or 1 white, 2 whites, 3 whites, 4 whites. So this is the only case. If you count the number of whites, this is the only case where you cannot do it, because if you have 0 whites, then it's all black. It's already all black. If you have one white, you can change that to black, and you have all black. And here is the other way around. You already have it all white, or you have only 1 black that you can change to white. So we can try all the options. So the top left corner is going to be either 0 or 1, right? So we determine the upper left corner of our 2 by 2 squared, and we're going to add. So we're gonna go over all the. So this goes from R to R plus 2, and this goes from C to C plus 2. And we want to see if the grid, well, we want to add 1 if the grid at R2, C2 is, let's say, white, any of them. And if it is different than 2, it means that we can change it. So we already found an answer, so we return true. Otherwise, we return false. Cool. So I guess we could even do we can even do this as a one-liner. So if we move this here, and then we do the two things here, and we say if any of them satisfy the condition, then it is true. Yeah. So that's a pretty long one-liner. Hey, Ray, welcome. That's a pretty long one-liner, but it's a one-liner anyways. All right, so let's go to question number 2. Lol. Yeah, that's why some people, so it's very useful to use the any. Well, I mean, in this case it wasn't worth it, I think, but in many cases it's worth it to use all and any and some, of course. In Python, that's one of the strengths of Python, that you can do that. Otherwise, in other language, if you don't use it, you sometimes have to have flags, Boolean flags, and change them and break, or you have to add more functions. All right, so right triangles. You're given a 2D Boolean matrix grid. Return an integer that is the number of right triangles that can be made with 3 elements of grid, such that all of them have value of 1. And here we have a definition of a right triangle. One of its elements is in the same row with another element, and in the same column with the third element. The 3 elements do not have to be next to each other. All right. So here we have examples where we have this 3 or this, and here we have only 2. Well, they are enumerated here. So let's see what we can do. So you can think of, you should notice that the orientation of the right triangle can be any. I think on this one I misunderstood the constraint that the 3 elements don't have to be next to each other. Connelliad, welcome. Hi. You misunderstood the constraint? But do you understand it now? So here's an example. So these 2 are not next to each other, and here the 3 of them are not next to each other. So it could have any of 4 orientations, right? So it could be like this. Well, sorry, I'm not very good at drawing here, but it could be like this, where it has the right angle on this side, or it could be like this, where it has the right angle here, or it could be like this, or it could be like this, right? So these are the 4 orientations that it could have. So let's consider our grid, right? So yes, this is a kite. So let's consider one one cell, right? And let's say that that cell is let's say that that cell is a 1, right? Because we need them. So this is going to be one of the corners of our triangle. Okay, so it must be a 1, right? So let's say that we focus first on this orientation. That means that it should have one corner to the right and one corner up. Okay, so that means that, so let's say that we have here, we have a 0, then here we have a 1, 0, 1, and 1. So that means that for the right, on the right side, we can choose any of these 3 positions. And then let's say that here it has a 0, then a 1, then another 1, 0, and so on. So here we could choose 2, and all these choices are independent. So we could choose this and any of these 2, right? Creating this kind of triangle, or we can choose this one, and again we can choose any of these 2, and so on. So here, since we have 3 to the right and 2 up, the number of right triangles with this orientation are going to be 2 times 3 are going to be 6, right? And the same thing happens with all the other combinations, right? So we have so one way we could write this. So for the given, let's say we call the number of ones here, we call them R. The number of ones here, we call them U. The number of ones here, we call them L. And the number of ones here, we call down, D. And so here, the squares, the right triangles with this orientation are going to be left times up. Then we have this orientation, which is going to be L times, oh, sorry, I think this one was right. Right up, left up, or right down plus left down, right? These are all the 4 combinations for the current one, right? So, but notice that we could, this is equal, we could take the common factor here. So here U is a common factor, so we can say this is U R plus L, and here the common factor is D. So again, this is R plus L, and now the common factor is this and this, so we have R plus L times U plus Z. So this is the expression. And notice that L plus R is just the number of ones in the row. So let's say this is row R, and this is called C. And so this is the number of ones in the row, and this is the number minus 1, right? Because we're not counting the 1 in the middle. And this is the number of columns of ones in the column, right? So let's say, so this is like let's say that we have a row which is going to have the number of ones in row R minus 1, because we don't want to count the 1 in the middle, times the number of of ones in the column C minus 1, because we don't want to count the 1 in the middle. And this is going to give us, this is going to be our expression. for all the triangles that have this. Hey, thanks for the follow. I can't read the name, but thank you for the follow. Okay, so notice that we only need to pre-compute the number of ones in each row and the number of ones in each column, and then we just go over and we add this multiplication, and that's going to be our result, right? So let's do the usual sizes, and here we have to get the sum of the row for each row, and then we want the sum of the column okay, so now we have the sum of the ones in each row and in each column. So now we can just sum this. So we go over each of the cells, and if it is a 1, well, if it is a 1, then we want to have this expression that we wrote, which is row R minus 1 and col C minus 1. Okay. All right. Pretty clean code once we have the cool. Thank you. It's more mathy than I'd expected. Yeah, I mean, you don't have to do the simplification, I guess. You could do it in a different way. I think this is the simplest way that I know. But no, yes, but we did this simplification here and this to make the code simpler. Like once you know that, you can just make the code pretty short, like we have here. Otherwise, you would have to do something longer. But yeah. All right, so let's go to question 3. So question 3 and question 4 are the same, but with different constraints. Find all possible stable binary arrays, part 1. You're given 3 positive integers, 0, 1, and limit. A binary array is called stable if the number of occurrences of 0 in R is exactly 0. The number of occurrences of 1 in R is exactly 1. Each subarray with a size greater than limit must contain both 0 and 1. Yeah, this is a convoluted way of saying that you can have consecutive groups that are longer than limit, size limit. Return the total number of stable binary arrays. Since the answer may be very large, return in mod this prime number, the usual. And here the constraints are all the numbers are up to 200, and in Q4 they're up to 1000. So what does that mean? That means that here we probably have to do something cubic right? Because 200 cubed is for 8 million, right? Whereas here you can, that would be too slow. So, and here you could do something quadratic, right? Because that would be 1 million. And so it's important to know how to extract the hints from the constraints. So here, if we can do something, let's write this here. So if we can do something cubic, then maybe we can do some DP, like, well, let's think about it this way. So notice that we have to count we have to count sequences of zeros and ones. So let's say that limit is 3, and so notice that we can create the sequence by setting the groups of consecutive values. Like, for example, we could start with 0, 0, right? So we have a group of size 2, and then we have a group of ones, right? They cannot exceed 3. So let's say we add a group of 3. It cannot be 4, for example. And then, so we're going to be alternating between groups, right? And so if we think about it this way, maybe we can have a count function that tells me how many of the, so let's say that I have count 1 and count 2, right? 2 numbers, right? And this is the total number of elements that I have to put in the sequence, given that that the first group is going to be of this kind, right? So that means that, so there's the base case. So if I don't have to put any more elements, so if this is 0, then there's only one sequence, right? The empty sequence. But otherwise, we want the size of our group. So for n in range, so the size of our next group is limited by C1 and by limit, right? So the group must have size at least 1, and at most the minimum between limit and C1. And since this is exclusive in Python, we have to add 1 so that we actually get to that value. And so now we have to count so now we will alternate. Now then after this group of C1, we want a group of C2, right? So now the first variable is going to be C2, and from C1 we want to subtract n because we set n values in the current group. So we add this, and this is our answer, right? And then we want to call count of 1 because we can start with ones, a group of ones, or we could start with a group of 0, in which case we call it this way, right? So this is going to be our DP, our recurrence. Yeah, notice why do I say DP? So here I just explained how the recurrence would be, but yeah, notice that the number of subproblems, so the number of subproblems is going to be, so there C1 can have 200 values, so it's 200 squared. But then here we're iterating, so the number of transitions is also 200. So this is equal to 200 cubed, which is what we wanted, which is 8 million. Okay, and that's good enough. So we can implement so this is C1 and this is C2, and so if this is the case, we finish, and the size of the group of the next group is between 1 and the minimum between C1 and limit, and here we want to count C2, C1 minus n, and here we want to count 0, 1 plus count 1, 0. And we have to cache, of course, don't forget that. And this is it, pretty straightforward DP. All right. So any questions about this one? Cool. So notice that we are alternating. Not really, it was clear. Thanks. Great. Okay, let's go to Q4 then. So this one is it's the same problem, but now we have to do something quadratic, so it's a little more complicated. Just a little bit. So let's see what we can do. So notice that if we knew how many groups my string is going to have, then the problem, then we can, so let's say let's say that we have, I don't know, 5 groups of 0, right? Then the number of groups, notice first that the number of groups of ones has to be either one less, right? So, or one, or the same, or one more. Once you set the number of groups of 1, the other one is limited. It has to have a difference of 1 at most. But let's say that we know how many. Once we know how many groups we're gonna have of one number, then the problems, we can count the zeros and the ones independently, right? Let's say that we have b groups of 0 or 1, it doesn't matter. Then this becomes this is similar to a very well-known problem of combinatorics, where you have it's called stars and bars, where you want to distribute here the number of you want to distribute balls in indistinguishable balls into bins that are distinguishable. So here we have 2 groups, 1 and 2, and we want the number of balls would be the number of zeros that we have, right? So maybe we can put 1 here, 1 here, 1 and 2, but so the way of solving this is with the combinatoric number. So you can encode this with stars and bars, like the name says. So here you would have 1 bar dividing the 2 boxes. So you have 1 less bar than boxes. And so the ways of distributing this becomes, so here we have 5 balls, so we would have 5 stars. And we have 1 division between the 2 boxes, so that we would have 1 bar. And the number of ways to distribute this would be the total number of permutations of this string with duplicates. And hey, El Santo, thanks for the subscription. Thanks a lot. So here, the formula for this. So notice that we have 6 places, and we want to find. We want to choose 1 for the var, for example. We could also choose 5 for the stars. It's the same thing. So here the answer would be choosing 1 out of 6, which is written using this notation. And this comes from if we call n the number of stars, we're going to have the total number of places here is going to be n plus b minus 1. Remember, because we have 1 less divisor of the boxes, the number of boxes. And then here we have, let's say, b minus 1, because we want to choose the places for the bars, right? So this is a very well-known formula. You can Google this, stars and bars, to learn more about it. I'm not gonna dive too deep into it. So, but here there's a problem, right? Because here we have the limit, right? So we're gonna count. So let's say here that the limit is 2, right? So this is invalid because we are adding 3. Nice, it comes up relatively often. Yeah. So here we're adding 3 balls into this box, right? Which means that we're gonna have a group of 3 zeros, but the limit is 2, right? So this is bad. So how do we do? So we're counting some configurations that are invalid. So one strategy to count this is to first, we're going to count all the distributions like with this formula that have no restriction, right? We're going to add, we can add more balls. We can exceed the limit, right? But then we want to subtract all the configurations and only the configurations that are invalid, right? And that's going to give us the valid configurations. And one way of doing that is to define sets of configurations. So let's say we defined the set A of I, which will have all the configurations that have at least limit plus 1. Let's call them balls here. In bin I, right? And no restriction in the other bins. Okay. So then this is a little complicated. I don't want to so explaining the whole solution would require without requiring any knowledge, any previous knowledge, will require a longer class than I was expecting to do. But here, let's see what I can do. So let's say that we want to compute the union of all these sets from 1 to n. Remember that this all comes when we fixed the number of bins, right? The number of groups. Okay, so here we want to compute the union of these sets. Okay, so here we can use the principle of inclusion, exclusion, and this is something that I explained in a previous class, which is based on this idea that if you want to compute the union of 2 sets, you can compute so the number of elements in the union is the number of elements in one of them plus the number of elements in the other minus the number of elements in the intersection, because you count them more than once, you count them twice here. And this formula generalizes to any number of sets, which is called this principle of inclusion-exclusion. And we are going to have all the combinations. You go over all the combinations of all the subsets, which here we have n of them, right? So the combinations are going to be a lot of them, but that doesn't matter because we can say, for example, we only care about how many of what the size of the set is, right? So if we have if we want to consider the subsets of these sets that have q elements, there are this many ways of choosing which of the subsets we're going to consider, and then they all have the same way of distributing the balls in the bins, right? Because we want to we have n balls, but we want to subtract k from the q. The q will have limit yes, we assign for all the q bins, which are the ones that have at least limit plus 1 balls already. So we subtract that from the total, and then remember that we don't want any of the groups to be empty, so we also need to subtract b, and those are how many balls we are left to distribute. So I think with this idea we can start coding. So let's first focus on the problem of counting the number of ways of assigning of distributing the zeros or the ones into groups that don't exceed the limit, right? So we're gonna count for each number of groups. The number of groups could be between 0 and, well, I mean 0 is not valid, but from 1 to n inclusive, right? If we have 10 zeros, one way is to have 10 groups of 1 0 each. So that's why we want to go up to n inclusive. So then the number of bins or groups are going to go from 1 to n plus 1 inclusive, and then we want to choose the number of bins that are definitely going to exceed the limit, right? And so those can be between 0 and b inclusive, which is the number of bins. So if the number of balls is less than the number of bins, so remember we have to put 1 ball in each bin because none of them have to be empty. then we have to put limit balls into each of the queue bins that we chosen. And so if we don't have enough balls, then we break, because if we don't have enough balls for this queue, if queue gets bigger, we won't have we still won't have enough balls. And then here we want to count the contribution of this term that, remember from the principle of inclusion exclusion, the sign of this term is going to depend on the number of, it's going to be alternated by the parity of the number of the size of the intersection that we are, the number of subset of the number of sets that we have in this intersection. And so here we want to choose from the beans the ones that will definitely exceed the limit times, and we will use here the multi-choose, which is it's just a way of using this formula here, the formula for the stars and bars. I call it multi-choose because I saw that name in somewhere and I liked it. And so here we have to say how many balls and how many beans we have. So balls are going to be n minus what we have here, right? And then the number of bins, the number of boxes is going to be b. And remember that we want to mod this. We want to mod the multiplication, and then we want to mod the addition, right? And so, okay, so this is the harder part of this problem, which depends on this principle of inclusion exclusion. You can search it, look it up. Principle of inclusion and exclusion to learn more about it. Then how do we use this? So we do this with the zeros, and we do this with the ones, right? So like I said, we can distribute the zeros and the ones independently. And now let's say that we first determine how many groups or bins of zeros we're gonna have from 1 to 0 inclusive, right? And then remember what I said, that the number of groups of 1 now is limited to a distance of 1 from the number of groups of zeros, right? So this means that it should go from here to here, right? So it can be -1 or the same or +1. But we want to check that the number of bins of ones is less than the total number of ones that we have to distribute. And now here we have the count of 0 for this number of bins times the count 1 of ones for this number of bins. And but we need to take into account that if they are the same, if the number of zeros beans, groups of zeros and the groups of ones, if they are the same, we could have them in two orders, right? We could have the zeros first or the ones first. So if that is the case, we are going to multiply by 2. Otherwise, we don't. And we mod the multiplication, we mod the addition. Okay? And so this is it, but now we have to implement the choose and the multi-choose functions, right? So the multi-choose function is pretty trivial, is what I wrote there. I mean, based on the other function, is just choose of n plus k minus 1 and k minus 1. Okay, this is all there is to it. Now to compute the, remember how the choose function the formula is n factorial divided by n minus k factorial and k factorial, right? So it's a product of factorials. So, but we have to do it mod. So one way of doing it is to pre-calculate all the factorials here. So the numbers are up to 1000. So let's say let's have that constant here, and let's pre-calculate. So remember that whatever we do here is going to be done only once for all the test cases. So it's better to have them here. So we can compute all the factorials up to m inclusive, up to 1000 inclusive. But mod. And then we want also to divide by factorials. So that means in mod, when you divide, you compute the inverse, the modular inverse, which in Python you can do it with the po function. So you calculate the power to the -1 power, and that will give you the modular inverse. Okay, so now we have the factorials, and so if we have to choose more than what we have, then it's 0. Otherwise, it's the factorial of n times the inverse factorial of n minus k. And let's mod here. And then times the inverse factorial of k, and mod again. And I think that's all the code we need. So we passed the examples. And we passed the systests. And we beat 95% of the solutions. That's cool. All right. So, yeah, that one, nice. Yeah, thank you. This one was hard. Yes. Yes, I think I should have prepared. Well, I mean, it's hard to explain things without assuming some base knowledge. So I already went over in more detail into the inclusion-exclusion principle. So maybe you can watch that video as a prerequisite for this one. But this one, even if you know the previous lesson, this one is more involved. It's more complicated, but it wasn't too bad. I mean, the code is pretty clean, I think. So yeah, that's all I have for this contest. Lucia, did you have any questions about this one? Yep. You have questions? Did you follow everything? That was all? You mean the yup was all? All right. So let's see who we can. Yes, essentially I don't have questions. All good. Well, I feel that I accomplished what I wanted. If someone understood the solution. Let's see if we can rate someone. I think in roses is
getting 6. Expected 3.
Is streaming LeetCode. So I'm gonna rate him. So thank you guys for watching, and see you on the next one. Bye bye.